Okay, so welcome back. So now what we're going to do is we're going to talk about second order derivatives today. And so we know what the first order derivative, the first order is the first derivative. Okay, so we're going to talk about first order derivatives of parametric curves or parametric equations. And so before we do that, let's go back to the first order derivative of parametric equations. So how do we get there? Okay, because with respect to t, so we have this derivative, right? dy dx, normally, right? The slope. Okay, the derivative of a function f of x is given by dy dx. Okay, so we take the derivative of the function y, right, which is a function in x, and we take the derivative with respect to x. Okay, and so we saw in the theorem that this is equal to dx, or excuse me, dy dt over dx dt. Okay, and in the theorem, what do we have here? We have and we gave the proof, right? I gave a proof of how we got there. Okay, so let me do it a little bit differently this time, and I'm going to use the chain rule in a different way. Okay, to get to the same result. Okay, because I want to take the derivative of this thing with respect to t. Okay, and so in essence what I'm doing is I'm using the chain rule by splitting this up this way. So I go dy, now I introduce the parameter I want to take with respect to t. I want to take the whole thing, the derivative with respect to t. Okay, so then I get dy dt, right? That's the capital F prime of f of x. Remember the chain rule? So, but I can also write it this way in Leibniz notation. Okay, so dy dt times dt dx. And then of course I can write this as a quotient by flipping this down to the denominator and taking the reciprocal. So that's where we get dy dt over dx dt. Now, we're talking about second derivative. So now what we're doing is we're going to say, okay, well, now we want to take the second derivative of the parametric equations. Okay, so that's what we call the second order derivatives. Okay, so how do we get there? Well, in this case, what we want to do is we want to take the second derivative, which means we're going to take the derivative of, right? So we want to take the derivative with respect to x of dy dx, the first derivative, right? But this is in terms of x. So let's use the same thing that we did here to get the second order derivative. So let's use the chain rule here. Okay? So this is going to be what? This is equal to d dx, and then what? Oops, sorry. dt, and then what? dt dx. So I just use the chain rule on this. So I'm introducing the parameter, and so I'm using the chain rule of what? dy dx. So what is this? Well, this is what? How do we do this? This is the second derivative. Okay, I'm using Leibniz notation here. So it's the second derivative of y with respect to x. And so this is the Leibniz notation that we use for the second order derivative. D squared y over dx squared. Okay, this is equal to this. And now I'm using the chain rule to break this piece like this. So again, same thing. Now watch what happens. I'm going to do the same thing that I did up here. I'm going to flip this down to the bottom. So this equals the derivative with respect to t, okay, over of dy dx, and this is going to go to dx dt. And we're done. So in other words, I can write this as the derivative with respect to t of dy dx divided by dx dt. Okay, and now if we know dy dx as a function of t, then this formula becomes very straightforward to apply. So let's do some examples. See you next time.